Hello, welcome back to Math 332 Linear Algebra. In this video, we are going to look at section 4.2, where we're going to study the concept called vector subspaces. So if you're given a set, let's say V, together with the usual additions and scalar multiplications, let's say they satisfy the 10 axiom. So we will call the V, sets V together with that two operation, we'll say that they form a vector space. So now you consider a set W, which is a subset of V. So the question is that subsets W together with that two operations that is from V, will that form a vector space or not? If that smaller sets W together with that two operations again form a vector space, which means they also satisfy that 10 axioms, then we will say that W is a vector space. But because W sits inside V, it's a subset of V. So in order to communicate that, we will say that W is a vector subspace of V. So we are going to look at all these concepts, and it is pretty abstract. And the problem is that a lot of students having trouble reading the sets notation and understand properly what is V and what is W. So we are going to look at a lot of examples to make sure that you know how to deal with this kind of problem. Okay. So it's going to be very interesting, and let's get right to it. All right, let's begin by looking at the objective for this section. So at the end of this video, you should know what does it mean that W is a vector subspace of V. And more importantly, given a set W, which is a subset of the vector space V, you should know how to determine that W together with the operation inherit from V, that whether it will form a vector subspace of V or not, okay? All right, so let's do a very quick review. So we are very familiar with this Euclidean space. This is Rn, which consists of all the vectors. It could be in column forms. It could be also in row forms, where the addition operation is defined this way and the scalar multiplication is defined this way. And when we study all the important properties for vectors that is in Rn, we realize that it satisfies this 10 property, and we're going to call this 10 property as the axiom for vector space, because now we are going to say that given any set, if we have a addition operation and scalar multiplications, and if the addition operation and scalar multiplications also satisfy this type of property, okay, then we will say that that set V together with these operations also behave as if you are in Rn. So we will call that new set together with the operations as a vector space. So this is what we have learned in section 4.1. Okay, so the example that we have seen in section 4.1 is that all these vectors, this is a polynomial of degree at most n, behave as if you are in Euclidean space Rn. You look at the matrices of size m by n, together with the usual matrix additions and scalar multiplication, also behave like the usual vector in Rn. And even like functions, real value functions, together with the usual function addition and scalar multiplications, also behave as if you are in Rn. So we will call all these sets together with their usual additions and scalar multiplications operations, and we'll say that all these are basically what we call vector spaces, okay? So these are the vector spaces that we have seen in section 4.1. So, okay, so the story for this section is pretty straightforward. You have given already a set V together with the operation additions and scalar multiplications. Let's say we know that this set V together with, this is our set V, together with the addition operation and scalar multiplication form a vector space, right? So we have seen notation like this. This is V, and then we have that, we have that. So this is a way to indicate that we have a set together with the operations, and given that this is a vector space, all right? So this is given already a vector space. So let's forget about the two operations here for a moment and just concentrate at the set. So let's say we have another set, which let's call W. All right, so W is a subset of V, right? In terms of just the set, W is a subset of V. Now let's look at the operations, the addition operation and scalar multiplications. Now look at all the elements that is in W, And make sure that you can add the elements in W using the additions operation and scalar multiplication that is defined for V. So now let's say that every element that is in W, okay, every element that is in W also inherit these two operations, meaning that you can take element that is in W. Okay, you can take one element that's in W, another one element that's in W, and you can add those elements using the operation here. You can also scalar multiply these elements using the operation here. So now the question is this W, okay, together with these operations inherit from V? So this W together with this operation inherit from V. Well, this again has a structure, that is outlined here. So which means that is this also a vector space? Okay, is this a vector space or not? All right. So if this is a vector space, it's cool. We can just call it a vector space. But sometimes you want to indicate that this is, even though it's a vector space, but it is sitting inside this bigger space. So in order to communicate that idea, we don't say that this is a vector space. I mean, we can say that, but we will say it more precisely. We'll say that W, it's a subspace. It's a subspace. Okay, it's a subspace of V. So when you say W is a subspace of V, meaning that W by itself is a legit vector space. It is a vector space, but because it is sitting inside V, so we say that it is a subspace of V. So if you recall from sections 4.1, in order to verify that W together with these operations is a vector space, you will have to better make sure that all the element in W also satisfy all these 10 properties, right? But in order to check subspaces, whether or not a set W, so this set W together with the operations that is inherit from this vector space V, so we are going to look at whether or not this as a set together with these operations, whether this will be a vector space. Our life is actually easier. We don't have to go through all these 10 axioms, okay? We don't have to go through all these 10 axioms because a lot of properties are inherent. For example, this property says that if you look at this, we know that this is a vector space. So every element in V, they are commutative under addition. So which means that every element in V, so take this 2, this U plus V is V plus U. If you take here, this U, this V, U plus V is V plus U. In particular, if you take UV here, that's in W, then U plus V is V plus U. So you can see that these properties right here is satisfied by elements that is in W, because you can say that this W inherit this kind of property. So this property is inherit. So this property is satisfied for element that is in W. But some of the properties are not. So for example, we need U plus V that is in V. So if you have U here, V here, so these are element that is in this big vector space V. And we know that because this is a vector space, so the sum of these two vectors will be still in V. Okay, so that's what it said. But if you take an element that is here, let's call this U, call this V, the sum of these two elements could be still in V, but it could be here. So your U plus V could be here. It doesn't violate this rule. It doesn't violate this rule. If you take two elements that is in W, so you take U here and then you take V here, the sum of these two elements has to be in V, but in V could be right here, right? So the element U plus V could be right here. It doesn't have to be guaranteed to be in W. So if you have two elements that is in W and you look at the sum is no longer in W, then this will never be a vector space, because vector space has to be closed under the addition operation and scalar multiplication. So you can see that this operation right here is dangerous. So this one is true for the bigger sets V, but it might not be true for the smaller sets W. Okay, so some of the properties are inherent, but some of the property are not. So which are the property that is inherent and which are the property that is not? So this one right here, as we can see, if it is true for all vectors that is in V, it is also true for all vectors that is in W. So this is fine. So this is also have to be true for all the vectors that is in V, which means that it also has to be in W. So this is also true for all the vectors that is in W. So here, this is also problematic because we know that V is a vector space, so they have a 0 vectors that is in V, but the 0 vectors could be right here. There's no guarantee that your 0 vector has to be in here, right? So this property here is not inherent, okay? This property here is not inherent, okay? So having a negative, so you have a vector here, which is U, all right? So the negative of U could be right here. The negative of U could be right here. It doesn't have to be guaranteed that it's in W, but they are still in V. So again, this is not considered inherent for elements that is in W. So this is also problematic. This is also problematic. If you have a vectors that is U right here, you take a scalar, multiply them. Well, it has to be in V, but it doesn't have to be in W. So your CU could get outside of W. So this is again a property that is not inherent. But this is a property that is true for all the vectors that is in V, so it will be also true for all the vectors that is in W. So this is okay. So this is inherent. This is fine. This is also fine. This has to be true for all the vectors that is in V, so it will be true for all the vectors in W also. So this is also fine. This is also fine. So you can see that in order to verify that W is a subspace or not, we actually don't have to go through the 10 properties because a lot of the properties are inherent. The only things that is not guaranteed is property 1. So property 1 is not guaranteed, okay? So property axiom number 4 is also no guarantee. Axiom 5 is also no guarantee. Axiom 6 is also no guarantee that will be hold for elements that is in W. So in order to check whether W is a vector subspace of V, we don't have to go through all the 10 axioms. In fact, we just have to verify that this 4, okay? Now we have a theorem which says that we don't actually have to do 4, we can do 2, and the rest will be the 4 and 5. So we just have to do 1, and then we just have to do 6, and 4 or 5. If you have 1, 6, you have 4, 5 also. That's the statements given right here in this theorem. So it says that you have already given a vector space. So this is already given a vector space, and you have a non-empty subsets W. Then this subset W together with the operations, okay, so the subset W together with the operations, which is inherent from V, okay, so this W is a subspace of V if and only if that's U. If you have U and V that is in W, so if you have U and V that is in W, you have U and you have V that is in W, you better make sure that U plus V is also in W. So if W is a vector subspace, if and only if we have this property, which is called closure under additions, right? So we want it to close inside W. So if you have closure under addition inside W, and you have closure for scalar multiplication inside W, then just by having these two, we will know that W is a vector subspace of V. So let me say that again, okay? So let's look at our setting again. So we have this, we have this, we have this. In order to verify whether W is a vector subspace of V or not, you just have to check closure under additions for all the elements that is in W, and you have to check closure under scalar multiplication for all the element that is in W, okay? So we basically have to check this closure properties under additions and closure properties under scalar multiplications. Now you might recall that how about the 4, 5, right? So isn't it 4, 5 is not inherent? But if you have this two property right here, closure under additions and scalar multiplications, we will have 4, 5 as well. Okay, the proof is right here. So remember that we need to have a 0. So we have scalar closure for scalar multiplications. So for example, if you choose, okay, so this is actually C. So if you have a U in W, so you have a U in W, all right? And we know that K of U or like C of U also have to be in W, all right? So we can choose C for any C, right? So we can choose C to be 0. So we know that U has to be in W, okay? The property B in the theorem says that CU will be in W. If you can have that, then property 4 will also hold because you can choose 0 as your C. So you will see that 0 is in W. So you will see that your 0 not only is in V, but it's in W. So if you have this statements, if you can prove that this statement is true, then you will have 0 inside W, okay? And how do you know that we have a negative inside W? Well, again, you can choose your C here to be -1. Then you will see that your negative U will be also in W. So the closure under additions and closure under scalar multiplications will guarantee that the property 4 and 5 will also hold. So at the end, you can look at the proof. So at the end, okay, so at the end, you will see that with these, in order to check W, is it a vector subspace or not, you actually don't have to go through all the 10 axioms. You just have to go through the 2 axioms. You just have to verify this 2 property, okay, this 2 property, which is written right here. So if you can verify this 2 property hold, then it is already enough to guarantee that the smaller sets W is itself a vector space, okay? All right, so let's give you a very quick example. And then for a slightly more complicated example, we really have to use this theorem. So this is a theorem that you're going to use a lot, so make sure you know. All right, so it's not a very complicated theorem. The statement is pretty easy. It just says that, hey, if you want to make sure that W is a vector subspace of V, you better make sure elements that is in W is closed under additions and also closed under scalar multiplications. Closure in mathematics always means that if you take some elements inside here, you do some operations, what you get, the elements that is in here, if you do addition operations, it will still be inside here. If you do scalar multiplication, it will still be inside here. It will not get out of W. It will not get out of W, okay? So you don't want things to get out from W. So remember, this is a very scary Japanese ghost movie where the ghost can, with long hair, and can climb outside the TV. This is not good. So this is not a closed operation. You don't want to watch a scary ghost movie where the ghost can actually climb outside of your TV and kill you. So we don't want it to happen. We want to have everything that is in here will stay inside here. We want a closure property. We want to have a closure property, okay? All right, so let's look at some example. So you have a vector space V, okay, with the addition operations and scalar multiplication. Sometimes we just drop the addition operation and scalar multiplication without mentioning it. We just say, hey, vector space V. But you have to understand that always means that we also have that 2 operations that is defined on it, okay? All right, so we know that being a vector space, we must have a 0 vector. So if you just look at a set which consists of that 0 vectors, this is trivially a vector subspace. It's actually a vector space. Everything's satisfied. This guy right here, if you scalar multiply, you will not get out of it. So you will see that this actually, if you use the theorem, you will see, even without using the theorem, it's trivial to see that this is a subspace of V. So this is the smallest subspace actually, and in fact, this is the smallest possible vector space, okay? So your vector space cannot be an empty set. The smallest vector space is actually a set consists of the 0 vectors with the addition operation and scalar multiplications, okay? All right, so we know that R3 is a vector space from section 4.1. So if you look at R3, so let's say this is a Z, this is a X and Y. So if we look at this set W, so you can see geometrically this set is this plane right here. This is basically your XY planes, all right? So this is basically your XY plane. And this is actually a subspace of R3. It itself, okay, this XY plane itself is a vector space, okay? And it is sitting inside R3, so we say that this is a subspace of R3. How do we know that? It's actually very easy to verify. You can actually verify that pretty easily. That if you take that element here, so let's say, okay, let's do it, okay? So let's say you take an element, okay? Let's say you take an element that's called U, which is U1 and U2. And let's say you take an element V, 0, okay? And then V1, V2, and then 0. So if you add them, okay? So if you add them, so what is U plus V? So U plus V will be U1 plus V1, U2 plus V2, and then 0. So obviously, this is still an element in W. So you take 2 elements that is in W, all right? You add them, it will be still an element in W. And if you take U, for example, and you scalar multiply them with any scalar, CU, let's look at what happened to CU. This will be CU1, CU2, and 0. Again, this is also an element in W. So this is very clearly a vector space, okay, a vector subspace, because using that theorem, we say that the closure property hold and the scalar multiplication property also hold, okay? So that should be pretty straightforward. I have a question for you now, actually. So if you look at a set, so this is a set that is in R2, okay? So this is a subset in R2 because in R2, we are looking at all the x, y without any restriction. But now we are actually looking at all the x, y which satisfy this, these conditions right here. So you will be able to tell actually, so this W, so it's not the entire R2, it's not the entire R2, it's actually this section only. X has to be positive, Y has to be positive. This is what you call your first quadrant. So this is obviously a subset of R2. The question is this itself a vector space? Okay, that's the questions. All right, let's take a moment to think about these problems, and you can pause the video, and when you think you already have the answers, you can restart the video and we can look at the solutions together, okay? Okay, welcome back, and I hope you get the right answer. The right answer is a no. So if we are looking at the first quadrant, we can easily pick a vector that is in the first quadrant. Let's say 1, 2. So this vector 1, 2 is in the first quadrant, but let's say I multiply a -3 towards this vectors, then the vectors 1, 2 will be somewhere right here now. And you will see that it would not stay inside that W. So this is not closed. Okay, so this is a set that is not closed under scalar multiplication, for example. Okay, so because of that, this W is not a subspace of R2. How about these questions right here? So if you have another set, which is obviously a subset of R2, so you have a Y, you have X. So this is looking for all the X and Y where the product is non-negative. So you will see that it basically will be all the elements that is in here. What do you think? Is this subset of R2 together with the usual operations, usual addition operation and scalar multiplications, will it be a vector space? Which means that will this W be a vector subspace of R2? All right, I would like you to take a moment to think about these particular problems, and you can pause the video, and when you think you already have the solutions, you can restart the video and we can look at the solutions together, okay? All right, welcome back, and I hope you already have your answers, and your answer should be no, okay? And let me show you one example. So for example, -1, -2, which is right here, the product of this -1 and -2 is positive. So it is an element that is in W. So this element that is in W, 5, 1 is also an element that is in W, but when you add them, you will get 4 and -1, and 4, -1 is somewhere here. 4 unit here, -1 here. So 4, -1 is somewhere right here. So you can actually have a vector that is in here and here, which is in W, but the sum of that two vectors does not go back to the sets W. So this is an example where the set is not closed, okay, under additions. So because they are not closed under additions by theorems, it is not a vector space, okay? It cannot be a vector space because for a vector space, you will have to be closed under addition, scalar multiplication, and satisfy all that 10x, the other 8 axiom, for example. Okay, so obviously we found one of that axiom that is broken, so it can never be a vector space. So that's the answer to the questions. Okay, so things are getting slightly more complicated. So usually students having trouble of understanding what the sets mean. So well, let's start by looking at this slightly complicated example, but not too bad. So you have a vector space R3, and you have something that is a subset of it. So W is definitely a subset of R3, right? Because every element in W is actually an element that is in R3. So we have R3, okay, and then we have W. And in fact, we can do better because especially if you have taken calculus 3 before, you know that this actually represents a plane that passes through the origin. So let's say this is your x1, this is your x2, this is your x3. So in your calculus, you usually call this is the x, this is the y, this is the z. All right, so you have a plane. So this is actually equation of a plane. 3x1 minus x2 plus x3 equal to 0. I can even ask you, if you already taken calc 3, I can even ask you that there's a normal vectors to that plane, and that normal vectors is in the direction of 3, negative 1, 1. Okay, so 3, negative 1, 1. So these are the normal vectors, so on and so forth. You don't have to know this for your linear algebra. I'm just saying for those who have taken calc 3 before. So your W is actually a plane that passes through the origins. So the question is, this subset, this something that's actually smaller than R3, will it also be a vector space or not? So we know they are sitting inside R3, which is a vector space under the usual vector addition and scalar multiplications. So we don't have to verify the 10 axiom. According to the theorem, we just have to verify that addition operation is closed under addition operation is closed and scalar multiplication is closed. Okay, right? Which means that if you take an element that is in W, take another element that is in W, you add them, make sure they are still in W. So this brings a very quick question. It's like, how do you show something, an element that is here, an element that is here, if you add them, that is still inside this set? So if you want to make sure something is inside this set, you will have to understand what qualifies to be in this set. Okay, so what qualifies to be in this set is that all this quantity, x1, x2, x3 here, cannot be any numbers. You have to satisfy this condition. So for example, we know that 0, 0, 0 is an element in W because 0 minus 0, 3 times 0 minus 0 plus 0 is 0. So this condition is satisfied. Remember, we talked about sets builder notation before. So this indicates the elements, and this is the description of what type of elements can be in this set. Okay, so in order to be in here, you have to satisfy this. Okay, so let's say, for example, 1, 1, 1. Is 1, 1, 1 an element in W? So let's see. 3, okay, times 1 minus 1 plus 1. So this is 3 minus 1, 2, right? So plus 1. So this is 3. So it is not 0. So the answer is not. 1, 1, 1 is not in W. So 1, 1, 1 probably is right here. That is not on the plane. All right. So in order to be in W, you have to satisfy these conditions. So let's take two elements. Let's take two elements out of W. So let's take two elements that is out of W. So let's say X, this vector X and this vector Y that is in W. What does it mean? Okay, immediately it means that 3x1, okay, minus x2 plus x3 has to be 0. This thing here is in W. Immediately it means that 3y1, okay, minus y2 plus y3 has to be 0. Okay, so let's add them. Okay, so let's add them. So usual vector additions give you this. So how do you know adding these two vectors will still be an element that is in W? How do you know U plus V will still be an element that is in W? That, okay, in order to be in W, we'll have to make sure that 3 times of this minus this, okay, plus this has to be equal to 0. So we have to verify that. So if you can't understand this, I'm not insulting your intelligence here, but this is to help you understand better. So we are looking for a box, okay, a star and a triangle, such that 3 times that box minus that triangle, okay, plus minus that star plus that triangle has to be 0. Okay, this is a pre-K version of linear algebra. So right here, this is our box, okay, this is our triangle. Star, and this is our triangle. So we will have to make sure that we need to have 3 times of the box, okay, minus the star plus that triangle. We have to make sure that it is equal to 0. So we have to verify that. So we take 3 times of this, okay, our box, minus our star, okay, and then plus our triangle. And please don't say that it is 0. We have to verify that, okay? So that's the key. So we want to see what happened to this, okay? So what happened to this? Okay, so let's distribute and regroup. So you will see that 3x1 minus x2 plus x3. Okay, we have the other one, 3y1 minus y2 plus y3. But your x1, x2, x3 is in W, so it satisfies these conditions. So this terms here is actually 0. Okay, and this part right here, okay, because this element is in W, So this quantity right here is also 0. So because this is 0 plus 0, so it is 0. So 3 times of this minus this plus this is actually 0. So this vector right here is actually W. So this is how you verify, basically checking the criteria, whether or not something belongs to a set. So you have to look at what qualifies to be in this set. So in order to be qualified in this set, you must satisfy this relationship. So you look at this and you ask, can I satisfy that relationship? If you have trouble with the x1 and the x1 here, the x3 with the x3 here, you get yourself confused, then make this a box, make this a star, make this a triangle. So you're looking for 3 times the box, okay, minus the star, okay, plus a triangle, and see whether or not it is 0. So the box, the star, and triangle can be anything, depending on what you are looking at. So we can actually, in this case, this is the things that we have to verify. So if it turns out to be 0, then this is good. This is an element that is in W. If it turns out to be non-zero, then it will not be in W. As simple as that. So for the theorem, the addition operation is actually closed. So we are good. How about scalar multiplications? So you take an element, okay, any real number, and then multiply with x. So this is how we usually multiply a vector with a scalar. And again, is this an element in W? So we have to verify. Okay, let's call this a box. Let's call this a star. Let's call this a triangle. So 3 times the box minus the star, okay, plus the triangle. Is it 0 or not? Well, you can see we have all the k, which is just a number. We can factor it out. And then we again have the 3x1 minus x2 plus x3. Okay, but your x right here, okay, your x right here is actually an element that is in W. So your x right here, that is element that is in W. So you have this, you must have this relationship, which means this thing right here is 0, which means this thing right here is 0. So you have k times 0, so it is 0. So having a k that is a real number and an x that is also an element that is in W, you have shown that kx is still in W. So you now have shown that the scalar multiplication is close. Okay, so by that theorem, W is actually a subspace of R3. Okay, so this is how you do it. And things is not so complicated if you understand how to verify an element, whether an element of a set, how is that element looks like. Well, if you do something, the new elements, is it an element of that set? You have to be able to check the criteria. So that is usually the difficult part for beginning students. So this is the things that you have to pay attention to, okay? Let me give you another example that is not R2, R3, but we are looking at the set of square matrices. So we know that this, okay, together with the usual matrix additions and usual scalar multiplication, we know this is a vector space. But now we are actually having a W, okay? So we are actually having a W, okay, that is smaller than that because we are looking at all the square matrices that commute with a specific matrix B. So you have a matrix B, okay? So you have a matrix B. This is fixed, okay? Which means that we don't know what that matrix is, but that matrix will not change. Okay, will not change. It's always the same B, all right? So this is always the same B. So you are actually looking for all the matrix A, square matrices, that will commute with this fixed vector B, okay? So you collect all of them and put it in this set W, okay? So let's, for example, think about what type of elements that is in W, okay? So I can tell you there are 2 very obvious elements that is in W. Okay, think about it. Do you see that one of the element that is in W is this? Okay, right? So I don't care what that matrix B is. I only know that this matrix B is 2 by 2. So a 0 matrix multiply B, you will get a 0 matrix. Okay, and if you take B multiply a 0 matrix, okay, right, you will also get a 0 matrix. Right? So what happened is that 0 matrix, okay, 0 matrix multiply B is equals to B times that 0 matrix. So the 0 matrix is actually an element in W. So this 0 matrix, okay, so this 0 matrix is an element in W. Why? Because, okay, you can call it A if you want to, because you can see now I have AB equals to BA. So matrix multiplication is not generally commutative, but that means that A times B is not necessarily B times A, but as you can see, there are some matrix that can have this commutative properties. Okay, we can have that. Do you see that we have another element that is in W? We also have another element that is in W. Okay, do you see which one is it? Okay, that's another one that you can also pretty easily see that it is also an element that's in W. Bear in mind that we have no idea what matrix B is, okay? We have no idea what matrix B is. We only know that matrix B is size 2 by 2. Now, I hope you see that the identity matrix, okay, is also an element that is in W. Why? Well, you can see if you take this, multiply with matrix B, that's by definition give you B, okay? And if you take B, multiply the identity matrix, this by definition is also B. So if you call this A, if you want to, you see that AB is equals to BA. So we don't really have to call it A, right? We know that we have a special notation for this. This is identity matrix. So we have IB, okay, equals to BI, right? So this matrix is an element that is in sets W. So we know that I is in W. Why? Because IB equals to BI. They commute with that matrix B. So we know the 0 matrix is in it. The identity matrix is in it. What else is in W? Oh, this is going to be a very tricky question. I actually have no answer to that because I don't know what B is. So, but we know that this is not an empty set, okay? This is not an empty set. So in order to apply the theorem, if you look at the theorems right here, these are main theorems that we're going to use throughout this video, is that we will have to take two elements from a set and make sure that they are closed under additions. We have to take one of the elements in the set and we have to show that they are closed under scalar multiplication. So you have to make sure that the set is not empty, otherwise you cannot take anything out of it. So one of the first step, if it is not very clear, okay, one of the steps that you have to demonstrate is that the set is not empty. And the previous example, we didn't really do that because it's obviously not empty. This is very easy to see. It's not empty. It's obvious to see this is not empty. But this kind of question is slightly more difficult now. And you will have to think about it. And actually, it's very good to try to figure out what type of elements is in it. So you can kind of see that there are two types of elements that's in it. It's definitely not empty. So we can take some element out and apply the theorem. So let's say we take an elements P and Q. So our P is in W, okay? What does it mean? It means that PB equals to BP, okay? Let's take another element that is in W. So if you're in W, what does it mean? It means that QB equals to BQ, okay? So our P and Q are not any 2 by 2 matrices. These are the 2 by 2 matrices that is coming from this set. So they commute with matrix B. That's what we have. So we add them. We want to add them, okay? So we add them, and we want to make sure that this is in W. Okay, what does it mean that this is in W? How do you show that the sum is in W? Well, if you want to show that it's in W, you have to make sure you satisfy these conditions. So you have to multiply with this B, and then you have to show, okay? You have to show that this is the same as B, P plus Q. You have to show that. If you can show this, then it will qualify that P plus Q is also in set W. So before you do anything, you need to know what you're supposed to do, right? Okay, so right here, this is what we want to do. We take P plus Q, multiply B. So matrix operation, we can distribute. That's the reason why you have that, okay? And PB, okay, is BP. Why? Because your P is in W, so they commute with B. QB is BQ. Why? Because again, right here, your Q is in W, so it commute with B. So now you have B on this side, which you can factor it out, and then you get this. So if you throw away the detail and you only look at this, then you have shown that P plus Q commute with B. P plus Q actually commute with B, so P plus Q is actually an element that is in B. All right, sorry, that is in W. So your P plus Q is in W. You take P in W, Q in W, you show that their sum is also in W. So it is closed. W is closed under additions. Okay, W is closed under addition. For the theorem, you have that closure under addition hold. All right. So how about scalar multiplications? Well, take a K, which is a real number. Take a P that is from W. So you want to show that KP is also in W, which means you want to show this. Okay, you want to show this. Okay, so this is what you want to show. All right, you want to show this. Okay. All right, so let's do it. KP times B. Okay, so using the associative law, we can do PB first. but your P is in W, so your PB is actually BP. So that's the reason why you see this. And these are just number. I can move that number inside right here. So I can get KP times B is B times KP. So obviously, now you see that your KP is also an element in W, which means that the scalar multiplication is closed, right? So the W is closed under scalar multiplication. Your sets W is closed under scalar multiplications. Therefore, we know that this sets W is a subspace of M2 by 2 because it is both closed under addition and scalar multiplications. Okay, now let me ask you this, okay? So if you are in this vector space, a polynomial of degree m most 2, and you are looking at something which is a polynomial of degree m most 2, but now our A, B, and C has to satisfy these conditions, okay? Question is your W is a subspace of P2 or not, all right? So you have a set. This is obviously a subset of P2. Think about what kind of elements that is in W. Well, for many elements that is in W, for example, 1 plus 0x minus x squared, okay, is in W. Why? Because this plus this equals to 0. So we have one element that is in it. 1 plus x squared is not in W, right? Why? Because, well, the coefficient doesn't add up to 0. Right, so you can see some of the elements that is in W and some of the element that is not in W, but clearly they are subspace, they are subsets of P2, they're subsets of P2. The question is, can you show that it is a subspace of P2 or it is not subspace of P2, okay? All right, let's take a moment to think about the problem, and you should pause the video. And when you think you have the solutions, you can restart the video and we will look at the solution together, okay? All right, welcome back, and I hope you have the answers. So the key thing is, how do you actually show closure under addition and closure under scalar multiplication? And a lot of times how you read these sets. A lot of homework problems and exam and quizzes you will see in the future is that how do you actually verify closure under addition and closure under scalar multiplication for many different types of sets. So the key thing is you have to understand the sets builder notations and have to understand what does it takes to be in W, okay? So in this case, okay, let's say you take two elements, P and Q, that is in W. So what does it mean? If P is written this way, it's in W, that means your P0 plus P1 plus P2 has to be 0. And your Q, right, is in W, which means Q0 plus Q1 plus Q2 has to be 0. So we add these two polynomial together. This is how you add polynomial. Now we investigate. This thing here, this thing here, this thing here, just the coefficients. What does it add up to? So these computations, you can see that if you regroup, you have this and you have this, and this is 0, this is 0. So you add up to 0. So, well, it qualifies to be in W. So this element here is in W. You can see linear algebra at this particular moment is very conceptual. The computation is a joke, right? The computation is a joke. You go to university, third year, this is a 300 level math, and what you do is you do 0 plus 0 equal to 0. So the computation is a joke, okay? It's the conceptual part. You have to get the concept, okay? The concept part is the difficult one. So you add it, and you want to know, does it in W or is it not in W? You look at what does it mean to be in W, okay? So you need to investigate all these coefficients. Does it add up to 0? So you investigate all these coefficients. Does it add up to 0? The answer is yes, because you have this, okay? So we have closure under additions. This is check, okay? All right. W is definitely not empty. We know that. We have closure under additions. Let's look at closure under scalar multiplications, okay? Take a number, take an element that is in W. You want to see whether or not this is in W. So this is how you multiply polynomial. So now this is your new coefficient, all right? If you want to see whether they are in W or not, well, you better make sure that this one, does it sum to 0? We don't know that. That's the reason why we are investigating. So don't say that it is 0 immediately, okay? You have to show it. So this one, you add them. Obviously, they all have a k that you can factor out, and you have that. And your P0, P1, and P2 is 0 because your P is not any P. Okay, your P is not any P in P2. Your P is in W. So we know that the coefficient here add up to 0. Okay, so we know that the coefficient add up to 0. So again, we have k times 0. So this is 0. So if you have k in R and p is w, what you have shown is kp is in w. So we have shown that the property B of the theorem hold, which means that we also have closure under scalar multiplications. So W is closed under additions. Okay, W is closed under additions. W is closed under scalar multiplications. All right, so W is closed under scalar multiplication. So by theorem, your W is a vector subspace of P2. Okay. All right, this concludes our discussion on this particular sections. And in the next sections, we are going to study the concept of linear combinations, the concept of span, the concept of linear independence. And at first, we are going to apply all these concepts to vectors, that the usual vectors that we know, which are vectors that is in R2, in R3, and in Rn. But you will see that actually we can also apply all those concepts very, very easily to, say, polynomial of degree at most 2, to matrices of size n by n, or to real value functions, so on and so forth, because all those mathematical objects, as we have seen, also behave as if they are the usual vector in R2 and R3 and Rn. So if you have a concept that can apply to the vectors that is in R2, R3, or Rn, you can also see that it will apply equally well to all those things that now we know vector spaces. So let's get to this interesting topics very, very soon. So I will hope you will appreciate that, and we'll see you very, very soon.